AT2019qiz burns in the constellation of Eridanus, a river of stars that winds across the southern celestial hemisphere, its light reaching Earth from a distance of approximately 215 million light-years, a span so vast that the photons arriving at terrestrial telescopes today began their journey during the late Triassic period, when the first dinosaurs walked the supercontinent of Pangaea and the ancestors of mammals were small, nocturnal creatures hiding in the undergrowth of cycad forests. This particular source of light, however, does not represent the steady nuclear burning of a star in the prime of its life, nor does it mark the explosive death of a massive stellar progenitor in the fury of a supernova, but rather something more gradual and in some ways more unsettling, a signature of gravitational violence unfolding over months and years rather than seconds, the systematic destruction of a star that wandered too close to the supermassive black hole residing at the center of its host galaxy, a galaxy that appears as little more than a faint smudge against the darkness when observed from Earth, yet which contains hundreds of billions of stars orbiting in their ancient patterns, most of them safe. Most of them maintaining stable distances from the gravitational monster at the galactic core, but this particular star, this single point of nuclear fire among countless others, found its orbit decaying, found itself drawn inexorably inward until the differential gravitational forces across its diameter, the tidal forces that increase as the inverse cube of the distance to the massive object, exceeded the star's own self-gravity, the gravitational binding that had held its constituent matter together. For perhaps billions of years, and in the span of hours, perhaps less, the star came apart, not in an explosion but in a stretching, a spaghettification as the closest portions of the star accelerated toward the black hole while the farther portions lagged behind. And the resulting stream of stellar material, hydrogen and helium and the heavier elements forged in the star's core over its lifetime began to fall inward, began to emit radiation across the electromagnetic spectrum as gravitational potential energy converted to kinetic energy and then to heat and light, and this brightening, this flare of electromagnetic radiation orders of magnitude more luminous than the star had been during its normal existence, reached its peak brightness in October of 2019, caught by automated sky surveys that scan the heavens nightly searching for transient phenomena, for anything that changes in a universe that often seems static from the perspective of human timescales, and thus AT2019qiz entered the catalogue of known tidal disruption events. The designation itself purely functional, indicating the year of discovery and a sequential identifier, but behind that alphanumeric string lies a story of stellar death and black hole feeding, a story that astronomers would piece together through careful observation and theoretical modeling over the months and years that followed, a story that would illuminate not only the physics of extreme gravity and accretion processes but also the hidden demographics of black holes in galactic centers, the complex relationship between galaxies and the massive objects at their hearts, and the detective work required to distinguish genuine tidal disruptions from other transient phenomena in a universe full of explosions and flares. The host galaxy itself, the stellar system within which this drama unfolded, presents as an elliptical or early-type spiral galaxy when examined in deep optical images, its structure dominated by older stellar populations that emit primarily in the redder wavelengths of visible light, with relatively little of the blue light characteristic of massive, young stars still fusing hydrogen in their cores, suggesting a galaxy that has largely exhausted its capacity for vigorous star formation, that has settled into a more quiescent phase of its evolution, though quiescent remains a relative term when discussing systems containing hundreds of billions of solar masses of material moving under mutual gravitational influence. The galaxy's redshift, measured through spectroscopic observations that reveal the systematic shifting of spectral lines toward longer wavelengths due to the expansion of space itself, places it at a comoving distance of approximately 215 million light-years, a measurement that accounts for the expansion of the universe during the time the light has been traveling, and this distance makes AT2019qiz one of the nearest well-observed tidal disruption events, close enough that ground-based and space-based telescopes can gather detailed spectra and light curves, can track the evolution of the flare over time with temporal resolution measured in days rather than weeks or months, can resolve enough detail to constrain theoretical models of the disruption and accretion process. At the center of this galaxy, inferred from the dynamics of surrounding stars and gas as well as from fundamental relationships between galactic properties and black hole masses, sits a supermassive black hole, an object whose mass measurements suggest a value of approximately 10 million times the mass of the Sun, though this estimate carries uncertainties that span perhaps a factor of 2 or 3. Uncertainties that arise from the difficulty of measuring masses at such distances, from the complexity of disentangling black hole gravitational influence from the gravity of surrounding stellar populations and dark matter, from the fundamental challenge of measuring something that emits no light of its own and reveals its presence only through its effects on surrounding matter and radiation. This black hole, like most supermassive black holes at the centers of galaxies in the present-day universe, exists in a relatively inactive state most of the time, meaning that it is not actively accreting significant amounts of matter, is not surrounded by a luminous accretion disk of the sort seen in active galactic nuclei and quasars, those beacons of the early universe that can outshine their entire host galaxies. The reasons for this quiescence relate to the environment surrounding the black hole, specifically to the absence of a steady supply of gas and dust being delivered to the innermost regions where accretion can occur. In elliptical galaxies and the bulges of spiral galaxies, stellar orbits are typically randomized, lacking the organized rotation seen in galactic disks, and this random motion makes it difficult for gas to lose angular momentum and spiral inward toward the center. Additionally, feedback processes from previous episodes of active accretion, episodes that may have occurred millions or billions of years ago, may have heated or expelled much of the gas that once resided in the central regions, creating an environment where fuel for accretion remains scarce. The supermassive black hole therefore sits mostly dark, its presence marked only by the subtle gravitational influence it exerts on stars passing thousands or tens of thousands of astronomical units away, stars that feel the black hole's gravity as just one component among many in the complex gravitational potential of the galactic center, and for these stars, orbiting at safe distances with stable trajectories, the black hole poses no threat, represents simply another mass concentration around which they orbit, much as planets orbit the Sun, though the scale differs by many orders of magnitude and the environment includes not a handful of objects but millions of stars within a parsec of the center. Occasionally, however, through processes that remain incompletely understood but which likely involve gravitational scattering from encounters with other stars or perturbations from massive star clusters or even interactions between the galaxy and neighboring galaxies, a star finds its orbit altered in such a way that its periapsis, its point of closest approach to the black hole, moves inward from a safe distance to a dangerous one, inward past what is known as the tidal disruption radius, the distance at which tidal forces exceed the star's self-gravity. This radius depends on both the black hole's mass and the star's properties, specifically on the star's mass, radius, and internal density structure, and for a solar-type star being disrupted by a 10 million solar mass black hole, the tidal disruption radius lies at approximately 50 to 100 times the Schwarzschild radius of the black hole, which itself is defined as the radius within which light cannot escape. The radius that marks the event horizon, the boundary of the black hole proper. The Schwarzschild radius for a 10 million solar mass black hole works out to approximately 30 million kilometers, roughly twice the distance from the Sun to Mercury's orbit, a scale that seems almost comprehensible when compared to familiar solar system dimensions but which represents the boundary of an object so gravitationally intense that space and time themselves become distorted beyond the possibility of escape. The tidal disruption radius, then, lies somewhere between 1 and 3 billion kilometers from the black hole's center, a distance comparable to the orbital radius of Jupiter or Saturn in our own solar system, and it is at approximately this distance that the star, having spiraled inward over perhaps millions of years through a series of gravitational interactions, having seen its orbit become gradually more eccentric until periapsis brought it fatally close, finally encounters gravitational forces that vary so strongly across its diameter that coherence becomes impossible. The physics of tidal disruption begins with the principle that gravity weakens with distance according to an inverse square law, meaning that an object twice as far away experiences 1/4 the gravitational force, and for a star approaching a massive object like a black hole, this means that the side of the star closer to the black hole experiences stronger gravitational attraction than the far side. For objects in stable orbits at comfortable distances, this tidal force remains negligible, easily overwhelmed by the star's self-gravity, the gravitational binding energy that holds the star's mass together against its own internal pressure. As the star approaches closer, however, as the distance to the black hole decreases, the tidal force increases rapidly, scaling as the inverse cube of the separation distance, and when this tidal force exceeds the star's self-gravity, disruption occurs. The critical distance depends on the ratio of the star's radius to its mass, on the black hole's mass, and on details of the star's internal structure, but for a solar-type main sequence star, a star similar to our Sun with a radius of approximately 700,000 kilometers and a mass of about 2 times 10 to the 30th kilograms, approaching a 10 million solar mass black hole, the disruption occurs at a distance of roughly 70 to 100 times the black hole's Schwarzschild radius, well outside the event horizon itself, meaning that the disruption is a purely tidal phenomenon, a pulling apart by differential gravity rather than by crossing some threshold related to the fabric of spacetime itself. The disruption process unfolds over a timescale determined by the star's orbital period at the point of closest approach, which for a star at the tidal radius of a 10 million solar mass black hole works out to a few hours, meaning that the star, which maintains structural integrity for billions of years, comes apart in less time than it takes for the Earth to rotate once on its axis. The process is not symmetric, because the star approaches the black hole along a particular trajectory, typically a highly eccentric orbit that brings it plunging inward from a much greater distance, and the tidal forces begin to stretch the star even before it reaches periapsis, elongating it along the direction toward the black hole, compressing it in the perpendicular directions, transforming what was once a roughly spherical ball of plasma into an increasingly elongated ellipsoid, and then, as the forces continue to increase as the star swings around the black hole, the elongation becomes extreme, the star stretching into a long filament, a stream of material that winds around the black hole following the star's original trajectory but now spread out over a much larger region of space. The leading edge of the stream moving faster than the trailing edge because it passed closer to the black hole and therefore experienced stronger gravitational acceleration. The material in this stream, this ribbon of disrupted stellar matter extending over millions or tens of millions of kilometers, consists primarily of hydrogen and helium, the dominant constituents of stellar atmospheres, along with smaller amounts of heavier elements, the metals in astronomical terminology. Elements heavier than helium produced either in the star itself through nuclear fusion if it was massive enough to have progressed beyond hydrogen burning, or inherited from previous generations of stars and incorporated into this star when it formed billions of years ago from a cloud of interstellar gas and dust. This material, which was gravitationally bound to the star and orbiting the galactic center as part of the star's overall trajectory, now finds itself on a variety of different orbits, because different parts of the star had different positions and velocities at the moment of disruption, and the subsequent evolution of the material depends on these new orbital parameters, on angular momentum and energy, quantities that were determined by where in the star the material originated and by the precise geometry of the encounter. Roughly half the disrupted material, the half that was trailing as the star swung around the black hole, finds itself on trajectories that remain bound to the black hole, meaning that the material does not have sufficient energy to escape to infinity but will instead fall back toward the black hole, though not immediately, not in a simple radial infall, because the material retains angular momentum from the star's original orbit, and conservation of angular momentum prevents matter from falling directly into the black hole, requiring instead that the material first lose angular momentum through some physical process before it can approach close enough to cross the event horizon. The other approximately half of the disrupted material, the half that was leading as the star passed periapsis, finds itself with enough energy to escape the black hole's gravitational influence entirely, shot outward on hyperbolic trajectories that will carry it away from the galactic center and out into the galaxy at large, where it will eventually dissipate into the interstellar medium or perhaps form new structures through gravitational instability over timescales of millions or billions of years, but in any case this material plays no further role in the immediate drama of the tidal disruption event, escaping before it can be accreted and therefore contributing nothing to the electromagnetic signature that makes the event visible across hundreds of millions of light-years of space. The bound material, however, the roughly 50% of the star's mass that remains gravitationally captured by the black hole, begins to fall back toward the black hole along its various eccentric orbits, and the timescale for this fallback depends on the orbital periods of different portions of the debris stream, with material that ended up on tighter orbits returning more quickly and material on more extended orbits taking longer, creating a characteristic fallback rate that increases from zero. At the moment of disruption, peaks after a time of roughly half the orbital period at the tidal radius, which works out to several weeks for a solar mass star disrupted by a 10 million solar mass black hole, and then declines following a power law in time. Specifically declining as time to the negative 5/3 power, a prediction that emerges from detailed calculations of orbital mechanics and the spread of orbital elements within the disrupted debris stream. As material falls back toward the black hole, it does not proceed directly to the event horizon but rather begins to circularize, to settle into more circular orbits in a process mediated by interactions between different streams of infalling material, streams that intersect and collide, converting the ordered kinetic energy of their orbital motion into random thermal energy, heating the gas to temperatures where it begins to radiate across the electromagnetic spectrum. This process, the formation of an accretion flow or accretion disk from the debris of the disrupted star, represents one of the most important phases of the tidal disruption event from an observational perspective, because it is this hot, radiating gas that produces the light curves and spectra that telescopes detect, that carries information about the black hole mass and spin, about the properties of the disrupted star, about the geometry of the accretion flow and the physics of matter under extreme conditions. The accretion disk that forms from tidal disruption debris differs in some respects from the accretion disks around supermassive black holes in active galactic nuclei, primarily because tidal disruption accretion is a transient phenomenon, fueled by a finite amount of material delivered over a finite time rather than by a steady supply of gas being channeled to the center through large-scale processes in the host galaxy, and this transient nature means that the accretion disk evolves significantly over the months and years following disruption, growing brighter as the fallback rate increases, reaching peak luminosity when the fallback rate reaches its maximum, and then fading as the supply of infalling material diminishes and the disk gradually drains through accretion onto the black hole or through other mass loss processes. The temperature of the accretion disk, and therefore the wavelengths at which it emits most of its radiation, depends on the accretion rate and on the black hole mass, with higher accretion rates and smaller black holes producing hotter disks that emit primarily in ultraviolet and X-ray wavelengths, while lower accretion rates and larger black holes produce cooler disks that emit more of their energy in optical and ultraviolet wavelengths. For a 2019 qiz, detailed modeling of the observed light curves and spectra suggests that the peak temperature of the accretion disk reached values of approximately 30,000 to 50,000 Kelvin, temperatures several times higher than the surface temperature of the Sun and sufficient to ionize most atoms in the gas, stripping electrons away and creating a plasma where matter exists as a mixture of positively charged ions and negatively charged free electrons, a state that allows the gas to interact strongly with magnetic fields and to emit continuum radiation through a variety of processes including thermal emission from hot gas, Bremsstrahlung radiation from electrons accelerating in the electric fields of ions, and recombination radiation as electrons recombine with ions to form neutral atoms, only to be ionized again moments later in the intense radiation field. The spectrum of this emission, the distribution of energy across different wavelengths, contains a wealth of information about the physical conditions in the accretion flow, and astronomers obtained spectroscopic observations of at 2019 qiz using ground-based telescopes equipped with spectrographs, instruments that disperse the light from the source according to wavelength, creating a rainbow-like spectrum where features such as emission lines and absorption lines appear at specific wavelengths corresponding to particular atomic transitions, and these features reveal the chemical composition of the emitting gas, the velocity of the gas through Doppler shifting of line wavelengths, the temperature and density of the gas through line ratios and line widths, and the geometry of the system through line profiles that reflect the complex kinematics of material orbiting a supermassive black hole. One of the most striking features visible in the spectra of at 2019 qiz, and indeed in the spectra of many tidal disruption events, is the presence of broad emission lines, features that extend over thousands of kilometers per second in velocity space, far broader than the lines seen in typical stellar spectra or in spectra of the interstellar medium, and this breadth indicates that the emitting gas is moving with a wide range of velocities, a natural consequence of orbital motion in the accretion disk, where gas at different radii orbits at different speeds according to Kepler's laws, with gas closer to the black hole moving faster and gas farther out moving more slowly, and when viewed from a direction not perfectly perpendicular to the disk plane. This range of orbital velocities produces a corresponding range of Doppler shifts, some gas moving toward the observer and therefore exhibiting blue-shifted emission, other gas moving away and exhibiting red-shifted emission, and the superposition of all these Doppler-shifted components creates a broad emission line profile whose width reflects the velocity structure of the accretion flow. The specific emission lines visible in AT2019qiz include the hydrogen-Balmer series, transitions from higher energy levels down to the second energy level in hydrogen atoms, with H-alpha at 663 nanometers and H-beta at 486 nanometers appearing prominently, along with emission from helium, from ionized oxygen, from ionized nitrogen. Lines that indicate the presence of elements heavier than hydrogen in the disrupted stellar material, elements that provide clues about the type of star that was disrupted, whether it was a main sequence star like the Sun, or a more evolved giant star with a different composition and structure, or perhaps a white dwarf. The dense remnant of a star that exhausted its nuclear fuel millions or billions of years ago and collapsed to a size comparable to Earth despite containing a significant fraction of the Sun's mass. Determining the nature of the disrupted star represents one of the key goals in studying tidal disruption events, because different types of stars produce different observational signatures when disrupted, differences in the total energy released, in the light curve evolution, in the spectral features. And understanding these differences allows astronomers to use tidal disruption events as probes of stellar populations in distant galactic centers, regions that are difficult to study through direct observations because individual stars cannot be resolved at distances of hundreds of millions of light-years. For AT2019qiz, the observed properties suggest that the disrupted star was likely a main sequence star, a star similar to the Sun in mass and composition, though possibly slightly more massive or slightly evolved off the main sequence, based on the luminosity of the event, which peaked at an absolute magnitude of approximately -19, meaning that the event shone with a luminosity roughly 100 billion times that of the Sun, outshining the entire host galaxy for a period of weeks. Around maximum brightness, and based on the evolution of the light curve, which followed approximately the predicted time to the -5/3 power decay after peak, consistent with theoretical models of fallback from a tidally disrupted main sequence star, and based on the spectral features, which showed emission from hydrogen and helium and heavier elements in ratios consistent with solar or near-solar abundance, the composition expected for a star that formed several billion years ago from gas that had been enriched by previous generations of stellar nucleosynthesis but not dramatically enriched beyond solar values. The initial detection of AT2019qiz came from the All-Sky Automated Survey for Supernovae, known as AUSUS-SN, a network of small robotic telescopes distributed around the globe that together image the entire visible sky roughly every 2 to 3 nights, searching for transient phenomena, and the system's automated pipeline flagged AT2019qiz as a new source, a brightening object that appeared where no source had been visible in previous observations, and this detection triggered follow-up observations by a variety of other facilities, including larger ground-based telescopes capable of obtaining detailed spectra, space-based telescopes operating in ultraviolet and X-ray wavelengths where Earth's atmosphere blocks observations, and radio telescopes that could search for emission from relativistic jets or other non-thermal phenomena. This coordinated campaign of multi-wavelength observations, beginning within days of the initial detection and continuing for months afterward, allowed astronomers to construct a comprehensive picture of the event's evolution, to measure light curves showing how the brightness changed over time in optical, ultraviolet, and X-ray wavelengths, to obtain spectra at multiple epochs showing how the emission line profiles evolved as the accretion flow developed and then began to fade, to place constraints on the presence or absence of jets, energetic outflows of material moving at speeds approaching the speed of light that are seen in some tidal disruption events but not in others, and to compare the observations with theoretical predictions from increasingly sophisticated numerical simulations that attempt to model the complex physics of tidal disruption and accretion. The ultraviolet observations, obtained primarily by the Neil Gehrels Swift Observatory, a space-based telescope equipped with ultraviolet and X-ray instruments that can rapidly respond to transient events, revealed that AT2019qiz was extremely bright in the ultraviolet, with peak luminosity in this wavelength range exceeding the optical luminosity by a significant factor, a finding consistent with the presence of a hot accretion disk with temperatures in the tens of thousands of Kelvin. Temperatures where the peak of thermal emission according to Wien's displacement law occurs in the ultraviolet part of the spectrum. The ultraviolet light curve showed the same general rise and decline as the optical light curve, but with subtle differences in the timing and shape that provide information about the temperature evolution of the accretion disk, specifically suggesting that the disk became hottest not at the moment of peak brightness but slightly before, during the rise phase when the accretion rate was increasing most rapidly and when the inflowing material had not yet had time to spread throughout the disk, but was concentrated in the innermost, hottest regions. As the accretion disk matured and material spread outward to larger radii where temperatures are cooler, the ultraviolet flux began to decline relative to the optical flux, a shift toward longer wavelengths that continued throughout the months-long fading phase, a spectral evolution that can be understood in terms of the decreasing accretion rate as the supply of fallback material diminished, leading to lower temperatures and longer wavelength emission. The X-ray observations of AT2019qiz, also obtained by Swift along with other X-ray telescopes including XMM Newton and NuSTAR, revealed a more complex picture, with X-ray emission detected at the onset of the event but exhibiting variability and spectral properties that suggest multiple emission mechanisms at work rather than a simple thermal component from the accretion disk. The X-ray spectrum showed evidence for both soft X-rays, photons with energies of a few hundred electron volts corresponding to temperatures of a few million Kelvin, and hard X-rays, photons with energies of tens of thousands of electron volts that cannot be explained by thermal emission alone but require additional processes such as inverse Compton scattering, where low-energy photons from the accretion disk collide with high-energy electrons in a hot corona above the disk and are scattered to higher energies, or Bremsstrahlung radiation from a very hot optically thin plasma, or possibly emission from a relativistic jet, though no strong radio emission was detected that would provide independent evidence for jet formation. The variability of the X-ray emission, with the X-ray flux changing by factors of 2 or more over timescales of days to weeks, suggests that the X-ray emitting region was relatively compact and subject to changes in physical conditions, possibly related to instabilities in the innermost accretion flow, to changes in the geometry or optical depth of the corona, or to variations in the mass accretion rate as material arrived in discrete streams or clumps rather than in a smooth flow, variations that might be expected given that the accretion is being fed by the debris of a disrupted star rather than by a steady inflow from a large-scale disk as in active galactic nuclei. The X-ray spectroscopy of AT2019qiz proved particularly valuable for constraining the physical conditions in the innermost regions of the accretion flow, regions where temperatures exceed millions of Kelvin and where relativistic effects from the black hole's strong gravitational field begin to affect the observed spectrum. High-resolution X-ray spectra obtained with XMM Newton's European photon imaging camera and reflection grating spectrometer revealed features consistent with thermal emission from an optically thick accretion disk, along with possible absorption features that might arise from winds or outflows driven from the disk surface by radiation pressure or magnetic forces. These winds consisting of partially ionized gas moving at velocities of hundreds or thousands of kilometers per second, carrying away a fraction of the accreted material and contributing to the overall mass and energy budget of the system. The detection of such winds has important implications for understanding the feedback processes by which black hole accretion affects the surrounding galaxy, because winds and jets represent mechanisms by which energy and momentum can be transferred from the immediate vicinity of the black hole, where accretion releases enormous amounts of energy in a tiny volume, to much larger scales where the energy can heat gas, drive shocks, and potentially suppress star formation by preventing gas from cooling and collapsing. The wind velocities measured in AT2019qiz, while substantial, fall short of the escape velocity from the host galaxy, suggesting that the wind material will eventually fall back and might participate in future episodes of accretion or star formation, though on timescales of millions of years, far longer than the duration of the tidal disruption event itself. Beyond the electromagnetic observations, AT2019qiz also became a target for neutrino detectors and gravitational wave observatories, instruments that search for signals in fundamentally different channels, neutrinos being nearly massless subatomic particles that interact only through the weak nuclear force and can therefore travel through vast amounts of matter without being absorbed or scattered, carrying information about physical processes occurring deep within dense regions where photons cannot escape, and gravitational waves being ripples in the fabric of spacetime itself, distortions that propagate outward from accelerating masses at the speed of light, carrying information about the dynamics of the most massive and compact objects in the universe. No neutrino detection has been confirmed for AT2019qiz, which is perhaps unsurprising given that tidal disruption events are not expected to be prolific neutrino sources unless significant particle acceleration occurs in jets, and the absence of strong radio emission suggests that AT2019qiz did not produce a powerful jet of the sort seen in some other tidal disruption events and in blazars, those active galactic nuclei where a relativistic jet happens to point nearly directly at Earth, producing extreme variability and high-energy emission through relativistic beaming effects. Gravitational wave detection for AT2019qiz was also not expected to be possible with current instruments, because while the disruption of a star by a supermassive black hole does involve asymmetric accelerating masses that should in principle produce gravitational waves, the amplitude of these waves is extremely small given the relatively low mass of the star compared to the black hole and the relatively slow velocities involved compared to events like binary black hole mergers that the LIGO and Virgo detectors were designed to observe, and the frequency of the gravitational wave emission from tidal disruption, corresponding to the orbital frequency of the star at the tidal radius, falls well below the sensitive frequency range of ground-based gravitational wave detectors, requiring instead space-based instruments like the proposed LISA mission that will observe at millihertz frequencies where supermassive black hole binaries and perhaps extreme mass ratio in spirals produce strong gravitational wave signals. The theoretical modeling of AT2019qiz and other tidal disruption events requires numerical simulations that solve the equations of general relativity to describe the spacetime geometry around the black hole, coupled with hydrodynamics equations that describe how the stellar material moves and responds to pressure gradients and gravitational forces, coupled with radiative transfer equations that describe how photons propagate through the gas, being absorbed and emitted and scattered, and these simulations demand significant computational resources, requiring massively parallel supercomputers running for weeks or months to simulate just the first few orbits of disrupted material around the black hole, and even with such resources, many approximations and simplifications remain necessary. Choices about resolution, about which physical processes to include and which to neglect, about how to handle regions where different physics becomes important, for instance the transition between the optically thick inner disk where radiation is trapped and diffuses slowly outward and the optically thin outer regions where radiation can escape more freely, or the treatment of magnetic fields that might be amplified through dynamo processes in the disk and might influence angular momentum transport, and energy dissipation through processes like the magnetorotational instability that is thought to drive turbulence and generate effective viscosity in accretion disks. Despite these challenges, simulations have made substantial progress in reproducing observed features of tidal disruption events, predicting light curve shapes that match observations reasonably well, predicting the formation of accretion disks with properties consistent with spectroscopic observations, and providing insights into aspects of the events that cannot be directly observed, such as the three-dimensional structure of the disrupted debris stream, the dynamics of stream-stream collisions, and the efficiency with which orbital energy is converted to radiation. One particularly interesting result from simulations of tidal disruptions concerns the role of the black hole's spin, a fundamental property that can range from zero for a non-rotating Schwarzschild black hole to a maximum value determined by the Kerr metric, the solution to Einstein's equations that describes rotating black holes, and the spin is quantified by a dimensionless parameter that ranges from 0 to 1, with higher values indicating faster rotation. The black hole's spin affects the tidal disruption process in several ways, most importantly by influencing the location of the innermost stable circular orbit, abbreviated ISCO, the smallest radius at which matter can orbit the black hole in a stable circular orbit without spiraling inward, and this radius depends strongly on the black hole's spin, lying at 6 times the Schwarzschild radius for a non-rotating black hole but shrinking to as little as 1 Schwarzschild radius for a maximally rotating black hole with spin parameter equal to 1, and this difference matters for tidal disruptions because it affects how closely material can approach the black hole before plunging inward, and closer approaches mean higher orbital velocities. More efficient conversion of gravitational potential energy to radiation and potentially different observational signatures in terms of light curve evolution and spectral properties. For a 2019 qiz, the observed properties place some constraints on the black hole's spin, though these constraints remain loose given the many other uncertainties in the modeling, suggesting that the black hole is probably not maximally rotating but could have a spin anywhere from 0 to perhaps 60 or 70% of the maximum possible value, a range that encompasses most theoretical expectations for supermassive black holes in galaxy centers, which are thought to grow through a combination of gas accretion and mergers with other black holes, processes that can either spin up or spin down the black hole depending on the geometry of the accretion flow and the orbital parameters of merging black holes. The accretion efficiency, defined as the fraction of the rest mass energy of infalling material that is converted to radiation before crossing the event horizon, depends critically on the black hole spin and on the structure of the accretion flow, with theoretical predictions suggesting efficiencies ranging from approximately 6% for non-rotating black holes to as high as 40% for maximally rotating black holes with accretion occurring in a geometrically thin, optically thick disk that extends down to the innermost stable circular orbit. For tidal disruption events, the actual efficiency realized depends on how quickly the disrupted debris can lose angular momentum and spiral inward, on whether a geometrically thin disk forms or whether the accretion flow remains geometrically thick and optically thin, on the role of magnetic fields in transporting angular momentum, and on mass loss through winds and outflows that remove material before it can be accreted. Observational estimates of the radiative efficiency for a 2019 qiz, derived by comparing the total radiated energy integrated over the duration of the event with estimates of the total mass that was bound to the black hole during the disruption, suggest an efficiency of a few percent, consistent with expectations for a moderately spinning black hole and an accretion flow that is not perfectly efficient at converting gravitational potential energy to radiation, with significant energy potentially being advected into the black hole rather than being radiated away, or being carried off by winds and outflows, or being used to drive jets if they were present but too weak to be detected. The long-term evolution of a 2019 qiz, extending beyond the first year after disruption, continues to provide information about the later phases of the event, the gradual transition from a bright, actively accreting state back toward quiescence as the last of the disrupted stellar material either accretes onto the black hole or is expelled from the system. Observations obtained several years after peak brightness show that the source has faded by several orders of magnitude in all wavelengths but remains detectable at levels still somewhat above the pre-disruption baseline, suggesting the presence of a residual accretion flow that is gradually dissipating, or possibly emission from material that was ejected during the disruption and is now interacting with the interstellar medium at large distances from the black hole, producing shocks and radiation through collision and heating. The rate at which the source fades during this late time phase provides constraints on the total amount of material that was bound to the black hole during the disruption, on the fraction of that material that successfully accreted versus the fraction that was lost through outflows or other mass loss mechanisms, and on the viscosity of the accretion flow, the parameter that determines how efficiently angular momentum is transported outward through the disk, allowing material to spiral inward toward the black hole. And while viscosity might seem like a mundane property, something familiar from everyday experience with fluids like water and oil, in accretion disks the relevant viscosity is not molecular viscosity but a turbulent or magnetic viscosity generated by instabilities and magnetic fields. And understanding this effective viscosity remains one of the major unsolved problems in accretion theory, relevant not only for tidal disruption events but for active galactic nuclei, for X-ray binaries where material from a normal star accretes onto a neutron star or stellar mass black hole, and for protoplanetary disks where planets form from the gas and dust orbiting young stars. The spectroscopic monitoring of a 2019 qiz during its decline phase revealed systematic changes in the emission line profiles that provide additional insights into the structure and evolution of the accretion flow, specifically showing that the lines became narrower and their peak wavelengths shifted slightly as the event faded, changes consistent with the inner, fastest moving regions of the accretion disk being depleted of material through accretion onto the black hole, leaving the outer, slower moving regions to dominate the emission, and additionally showing the emergence of forbidden emission lines, spectral features from atomic transitions that are suppressed in high-density environments because collisions de-excite the upper energy levels before photons can be emitted, but which become visible in lower-density environments where collision rates are lower and the atoms have time to undergo these transitions. The appearance of forbidden lines in the late-time spectra of AT2019qiz indicates that the gas density in the emitting region has decreased as the accretion disk expands and disperses, transitioning from a compact, dense structure immediately after the disruption to a more extended, diffuse configuration months and years later, and the specific forbidden lines observed, including lines from doubly ionized oxygen at wavelengths of 501 nanometers and 496 nanometers, provide additional constraints on the temperature and density of the gas and on the ionization state maintained by the radiation field from the central accretion flow. The host galaxy environment also plays a role in the evolution of AT2019qiz, because the galactic center where the disruption occurred is not empty space but a complex region filled with stars, with stellar remnants such as neutron stars and stellar mass black holes, with diffuse gas from stellar winds and supernovae, with magnetic fields threading through the interstellar medium, and with dark matter whose gravitational influence affects the orbits of all these components even though the dark matter itself does not interact electromagnetically and therefore remains invisible. The rate at which stars are delivered to the tidal disruption radius depends on the stellar density profile in the galactic center, on the velocity dispersion of the stellar population which determines how fast stars are moving and therefore how likely they are to have close encounters that perturb their orbits, and on the presence or absence of a central stellar cluster, a dense concentration of stars within the central parsec that some galaxies possess and others do not, depending on their merger history and the efficiency with which stars have been able to dissipate energy and sink toward the center through dynamical friction. In the case of AT2019qiz host galaxy, observations do not reveal a particularly dense central star cluster compared to some other galaxies, suggesting that the disruption rate in this system might be relatively modest, perhaps one event every 10,000 to 100,000 years, meaning that if one could watch this galaxy continuously over geological timescales, one would see similar flares occurring sporadically, unpredictably, as individual stars happen to find themselves on doomed trajectories, their millions or billions of years of stable existence ending in a matter of hours as they encounter the gravitational monster at the galactic heart. Detailed photometric monitoring of AT2019qiz, conducted by multiple telescopes over a baseline of more than 3 years following the initial detection, has allowed astronomers to search for periodic or quasi-periodic variations in the light curve that might provide evidence for orbital motion in the accretion disk or for precession of the disk itself if it is misaligned with the black hole's spin axis, phenomena that have been predicted by theoretical models but which remain challenging to observe because the expected periods range from days to months and the amplitude of the variations might be small compared to stochastic variability driven by turbulence and instabilities in the accretion flow. Analysis of the AT2019qiz light curve has revealed some evidence for quasi-periodic oscillations with timescales of tens of days, variations that could potentially be attributed to orbital motion at specific radii in the accretion disk or to instabilities that propagate through the disk on characteristic timescales, though the statistical significance of these features remains marginal and additional observations would be needed to confirm their reality and to distinguish them from random noise. Fluctuations. If genuine, such oscillations would provide powerful constraints on the accretion disk structure and on the black hole mass and spin, because the orbital period at a given radius is directly related to the enclosed mass through Kepler's third law, and deviations from Keplerian motion due to relativistic effects near the black hole depend on the black hole's spin and on the details of the spacetime metric. Comparing AT2019qiz with other observed tidal disruption events reveals both similarities and differences that provide insights into the diversity of these phenomena, the range of possible outcomes depending on the properties of the disrupted star, the mass and spin of the black hole, and the viewing angle from which the event is observed. Some tidal disruption events show strong X-ray emission with relatively weak optical emission, suggesting viewing angles where a relativistic jet is pointed nearly toward Earth, allowing observers to see high-energy emission that is beamed along the jet direction through relativistic effects, while other events show strong optical and ultraviolet emission with relatively weak X-rays, suggesting more isotropic emission dominated by thermal radiation from an accretion disk viewed from a range of angles, and AT2019qiz falls into this latter category, showing the characteristic broad thermal spectrum and moderate X-ray emission expected for disk-dominated emission without strong relativistic beaming. The light curve evolution also varies among events, with some showing faster rises and declines than others, differences that may relate to the internal structure of the disrupted star, with more centrally concentrated stars producing faster evolution because the spread in orbital periods within the disrupted debris is smaller, while more extended stars or evolved giant stars produce slower evolution because the debris spans a wider range of orbital parameters, and additionally some events show evidence for multiple peaks or plateaus in their light curves, features that might indicate clumpy accretion as distinct streams of material arrive at different times, or interactions between the accretion flow and pre-existing material in the galactic center. Or possibly repeated close passages if the star was not completely disrupted on the first passage but only partially disrupted, losing some of its outer layers while the core remained intact and returned for another close passage on a subsequent orbit. The spectroscopic evolution of AT2019qiz, tracked through dozens of spectra obtained at different epochs spanning from weeks before peak brightness to months and years after, shows systematic changes in the emission line profiles, specifically a broadening of the lines during the rise phase, a peak in line width near maximum brightness, and a gradual narrowing during the decline phase. A pattern that can be understood in terms of the changing velocity structure of the accretion flow as it develops, expands, and then contracts as the accretion rate decreases. Early in the event, when the first material is arriving and beginning to circularize, the emission might come predominantly from a relatively compact region near the black hole where velocities are highest, producing very broad lines, while later, as material accumulates at larger radii and the accretion disk becomes more extended, emission from the outer disk begins to dominate and the lines narrow somewhat because orbital velocities decrease with increasing radius, and finally, during the fading phase, as the inner disk drains through accretion onto the black hole and the outer disk becomes relatively more important as a source of emission, the lines continue to narrow, providing a kind of time-resolved tomography of the accretion disk structure. A way of using spectroscopy at different epochs to probe different regions of the system as the physical conditions evolve. Detailed modeling of these line profile changes requires consideration of the disk geometry, of the emissivity profile that determines where in the disk most of the line emission originates, of opacity effects that might cause photons from different regions to be preferentially absorbed or scattered, and of possible outflows or winds that might contribute blue-shifted emission from material moving toward the observer at high velocities, either driven by radiation pressure from the intensely bright accretion disk or launched magnetically through magnetohydrodynamic processes involving the disk's magnetic field. The question of jet formation in tidal disruption events remains an active area of research, because while some events clearly show evidence for relativistic jets through strong radio emission, rapid variability, and high-energy emission consistent with synchrotron and inverse Compton processes, many other events including AT2019qiz show little or no evidence for jets, raising questions about what determines whether a given tidal disruption will produce a jet. The formation of jets around black holes more generally is understood to require several ingredients, including a source of energy and angular momentum from the black hole itself or from the accretion disk, a mechanism to extract that energy and convert it to kinetic energy of outflowing plasma, typically thought to involve magnetic fields that thread through the black hole's ergosphere and tap its rotational energy or that extract rotational energy from the disk, and some process to collimate the outflow into a narrow jet rather than allowing it to expand isotropically, again typically attributed to magnetic fields that confine the plasma through magnetic pressure and magnetic tension forces. In the specific case of tidal disruptions, the jet formation rate appears to be low, with estimates suggesting that perhaps 10 to 20% of events produce detectable jets, and the reason for this low rate is not fully understood but might relate to the properties of the accretion flow formed from disrupted stellar material, which differs from the accretion flows in active galactic nuclei in several respects, particularly in its transient nature, its potentially lower angular momentum. If the star was on a nearly radial orbit before disruption, and its composition which is predominantly hydrogen and helium from the stellar envelope rather than gas with significant metal content that might affect cooling and magnetic field behavior. Radio observations of AT2019qiz, conducted with the Very Large Array and other radio telescopes, placed stringent upper limits on any radio emission from the source, limits that constrain the presence of relativistic jets or other non-thermal emission mechanisms and that suggest, though do not definitively prove, That AT2019qiz did not launch a powerful relativistic jet of the sort seen in a minority of tidal disruption events. The absence of strong radio emission is consistent with the moderate X-ray luminosity and the thermal-dominated spectrum, suggesting that the emission from AT2019qiz is dominated by thermal radiation from the accretion disk with minimal contribution from non-thermal processes involving relativistic electrons and magnetic fields, though it remains possible that a weak jet was present but simply too faint to be detected with current radio facilities, or that any jet was oriented such that it was not pointed toward Earth and therefore the emission was not boosted by relativistic beaming effects. Future radio observations with more sensitive instruments, including next-generation facilities such as the Square Kilometre Array and the Next-Generation Very Large Array, will provide deeper limits on radio emission from tidal disruption events and might detect weak jets that are currently below the detection threshold, allowing better constraints on jet formation mechanisms and on the fraction of events that produce jets. The role of AT2019qiz in the broader context of supermassive black hole research extends beyond its individual properties to its contribution to demographic studies, to understanding the population of black holes and galaxy centers across the universe, their masses, their spins, their accretion histories, and their impact on galaxy evolution. Supermassive black holes are thought to play a crucial role in regulating star formation in galaxies through feedback processes, where energy injected into the surrounding gas by accretion-powered radiation and jets heats the gas to temperatures where it cannot cool and collapse to form new stars, or expels the gas from the galaxy entirely, removing the raw material needed for star formation and thereby potentially terminating the galaxy's growth. This black hole feedback has been invoked to explain observed correlations between black hole mass and galaxy properties such as the stellar velocity dispersion and the luminosity of the galactic bulge, correlations that suggest a tight connection between black hole growth and galaxy evolution, though the physical mechanisms responsible for establishing and maintaining these correlations remain subjects of debate, particularly regarding how black holes that are tiny compared to their host galaxies, occupying regions less than a parsec across within galaxies spanning tens of thousands of parsecs, can exert influence on galactic scales, and the answer seems to involve the enormous amount of energy that black hole accretion can generate. With even a relatively small amount of accreted mass converting to energy with an efficiency of perhaps 10% through gravitational potential energy release, far more efficient than nuclear fusion which converts less than 1% of rest mass to energy, and this energy, when deposited into the surrounding medium through radiation, jets, and winds, can affect structures on scales vastly larger than the accretion disk itself. Tidal disruption events like AT2019qiz provide unique opportunities to study supermassive black holes that are otherwise dormant, that do not show the persistent emission characteristic of active galactic nuclei, and since the majority of supermassive black holes in the present-day universe are not actively accreting, tidal disruptions offer a way to detect and characterize these otherwise hidden objects, to measure their masses through modeling of the light curves and spectra, to place constraints on their spins through observations of the inner accretion disk, and to probe the stellar populations in galactic centers by identifying the types of stars being disrupted. The rate at which tidal disruptions occur in a given galaxy depends on the stellar density in the galactic center and on the black hole mass, with current estimates suggesting rates of roughly one event per 10,000 to 100,000 years per galaxy for typical massive galaxies, rates that seem low from the perspective of human timescales but which, when multiplied by the enormous number of galaxies in the observable universe, imply that hundreds or thousands of tidal disruption events should be occurring every year across the cosmos, and modern transient surveys with their ability to image large areas of sky repeatedly are beginning to find these events in substantial numbers. With several dozen well-observed events now in the catalogs and more being discovered each year as survey cadences improve and automated pipelines become more sophisticated at distinguishing genuine astrophysical transients from artifacts and known variable sources. The statistical study of tidal disruption event demographics has revealed some intriguing patterns, including an apparent preference for events to occur in certain types of galaxies, specifically in galaxies that have undergone recent mergers or interactions or that possess post-starburst stellar populations, galaxies that experienced vigorous star formation in the relatively recent past, within the last few 100 million to billion years, but which have since ceased forming stars at significant rates. The reason for this apparent preference remains unclear, but it might relate to the dynamics of stellar populations in the galactic centers of such galaxies, with merger-driven perturbations potentially scattering stars onto eccentric orbits that bring them closer to the central black hole, or with the presence of young stellar populations in the central regions creating a larger reservoir of stars that might be disrupted before they have time to relax into more stable orbits through two-body interactions and energy exchange with the surrounding stellar distribution. The host galaxy of AT2019qiz shows some characteristics consistent with this pattern, including morphological features that might indicate a past merger or interaction, though the evidence is not definitive and alternative explanations remain possible, including simply that the galaxy happens to be observed during a period when a tidal disruption occurred by chance, with no special conditions required beyond the statistical expectation that such events should occasionally happen in any galaxy. With a central supermassive black hole and a surrounding population of stars. The future of tidal disruption research promises significant advances as new observational facilities come online and as theoretical models become more sophisticated through improved numerical simulations and better understanding of the underlying physics. The upcoming legacy survey of space and time to be conducted by the Vera C. Rubin Observatory, previously known as LSST, will image the entire visible sky every few nights with unprecedented depth and sensitivity, discovering transient phenomena of all types at rates that will dwarf current surveys, and tidal disruption events will be among the beneficiaries of this data deluge, with estimates suggesting that LSST might discover hundreds or even thousands of tidal disruptions per year, allowing statistical studies of the population, studies of how disruption rates depend on galaxy properties, studies of rare subtypes such as disruptions of giant stars or white dwarfs, and studies of extremely distant events that can probe the demographics of supermassive black holes in the early universe where active galactic nuclei were more common and where galaxy formation was still ongoing. Space-based facilities such as the James Webb Space Telescope, with its infrared capabilities and high sensitivity, can provide detailed spectroscopy of tidal disruption events at wavelengths where dust extinction is less severe, potentially observing events in dusty galactic centers that are difficult to study in optical wavelengths. And forthcoming X-ray missions with improved sensitivity and spectral resolution will enable more detailed studies of the high-energy emission from tidal disruptions, probing the innermost regions of the accretion flow where relativistic effects become important and where direct signatures of black hole spin might be detectable through relativistic distortions of the X-ray spectrum. Gravitational wave observations also offer intriguing future prospects for tidal disruption science, though not through the disruption events themselves but rather through the possibility of detecting intermediate mass black holes in galactic centers through the gravitational waves they produce when capturing compact objects such as stellar mass black holes or neutron stars. These extreme mass ratio in spirals, events where a compact object spirals into a supermassive black hole emitting gravitational waves that sweep across a wide range of frequencies as the orbit shrinks, will be prime targets for the LISA mission, and while LISA will primarily focus on supermassive black hole binaries and galactic binaries of stellar mass compact objects, extreme mass ratio in spirals could provide exquisitely precise measurements of black hole masses and spins through the gravitational wave signal, measurements that could be compared with electromagnetic observations of tidal disruptions in the same systems to provide complementary constraints on black hole properties. The combination of gravitational wave and electromagnetic observations, the emerging field of multi-messenger astrophysics that has already proven transformative through observations of neutron star mergers, promises to open new windows on the physics of black hole accretion and on the dynamics of matter under the most extreme conditions accessible to observation, conditions where gravity is so strong that Newtonian physics breaks down completely and general relativity becomes essential for accurate description, where velocities approach the speed of light and time dilation become significant, where spacetime curvature affects the paths of photons and the propagation of gravitational waves, and where quantum effects might become important in the immediate vicinity of the event horizon where Hawking radiation, the theoretical prediction that black holes emit thermal radiation through quantum processes involving virtual particle pairs, might in principle be detectable, though the expected temperatures and luminosities for supermassive black holes are far too low for detection with any conceivable technology. The broader implications of tidal disruption research extend to fundamental questions about the nature of gravity, the behavior of matter under extreme conditions, and the ultimate fate of information that falls into black holes. A question that has troubled physicists since Stephen Hawking's work in the 1970s revealed an apparent contradiction between quantum mechanics and general relativity regarding whether information is truly lost when it crosses the event horizon or whether it is somehow preserved in the Hawking radiation emitted over the black hole's lifetime, a problem that touches on the foundations of physics and that remains unresolved despite decades of theoretical work. While tidal disruption observations cannot directly address this fundamental question, they do probe the region just outside the event horizon where strong field general relativity becomes essential and where any deviations from Einstein's theory, if they exist, might manifest in observable ways, and they provide laboratories for studying matter at densities and temperatures that cannot be reproduced in terrestrial experiments, densities where atomic nuclei are crushed together and where the distinction between protons and neutrons begins to break down, temperatures where matter exists as a fully ionized plasma with additional degrees of freedom from excited quantum states, and magnetic fields with strengths reaching millions or billions of Gauss, far exceeding anything achievable on Earth, and creating environments where the physics of magnetic fields, the behavior of plasma waves, and the efficiency of particle acceleration all enter regimes that remain poorly understood and must be inferred from observations of astrophysical systems. The theoretical framework for understanding tidal disruptions has evolved significantly over the past several decades, beginning with early analytical work that treated the problem using simplified assumptions about stellar structure and orbital geometry, progressing through increasingly sophisticated numerical simulations that could follow the complex hydrodynamics of the disrupted debris as it streams around the black hole and begins to circularize, and now incorporating general relativistic effects, magnetic fields, radiative transfer, and the coupling between different physical processes that all operate simultaneously in these extreme environments. Modern simulations of tidal disruptions run on some of the world's most powerful supercomputers, utilizing adaptive mesh refinement techniques that allocate computational resources where they are most needed, concentrating resolution in regions where density gradients are steep or where important physics is occurring while using coarser resolution in more quiescent regions, and employing sophisticated algorithms for solving the equations of magnetohydrodynamics on curved spacetime geometries. For tracking radiation through optically thick and optically thin media, and for following the evolution of the system over many dynamical timescales as the accretion disk forms, evolves, and eventually dissipates. These simulations have successfully reproduced many features of observed tidal disruption events, including the characteristic light curve shape with its rise and subsequent power law decline, the thermal spectrum with temperatures of tens of thousands of Kelvin, and the broad emission lines indicating high-velocity gas in the accretion disk, though significant challenges remain in matching all aspects of the observations simultaneously and in understanding the role of magnetic fields, which can dramatically affect angular momentum transport and energy dissipation but which remain computationally expensive to simulate with adequate resolution. AT2019qiz, observed in exquisite detail across multiple wavelengths and followed through its rise, peak, and gradual decline over months and years, stands as one of the best-studied examples of stellar destruction by a supermassive black hole, an event that illuminates the physics of extreme gravity, that reveals the hidden demographics of dormant black holes in galaxy centers, that probes the stellar populations in galactic nuclei through forensic analysis of disrupted material, and that contributes to our understanding of accretion physics in a regime where the fuel supply is finite and transient rather than steady and continuous. The event's proximity, by cosmological standards, and its intrinsic brightness allowed detailed follow-up observations that would be impossible for more distant events, observations that include dozens of spectra showing the evolution of emission line profiles, light curves in multiple wavelengths covering optical, ultraviolet, and X-ray bands, and searches for associated phenomena such as radio emission from jets and neutrinos from particle acceleration, and these observations have provided crucial tests of theoretical models, confirming some predictions, challenging others, and revealing unexpected features that spur new theoretical work to explain The continuing study of AT2019qiz as it fades back toward quiescence, the comparison of its properties with those of other tidal disruption events discovered by ongoing surveys, and the anticipation of future events that will be discovered in larger numbers and studied with next-generation facilities, together constitute a research program that promises to shed light on some of the most enigmatic objects in the universe, black holes that reveal themselves only through their gravitational influence. And through the radiation emitted by material in the process of being consumed, material that was once part of a star, that was forged in nuclear reactions over billions of years, and that spent its final moments stretched into a thin stream, heated to millions of degrees, and ultimately incorporated into the event horizon of a supermassive black hole, adding its tiny contribution to the black hole's mass and perhaps imperceptibly altering its spin, in a process that transforms ordered stellar structure into disordered thermal radiation and gravitational potential energy into light that streams outward at 300,000 kilometers per second, crossing millions of light-years to reach telescopes on Earth, where astronomers piece together the story of what happened in that distant galactic center 215 million years ago, when dinosaurs walked the Earth and the star that would become AT2019qiz was perhaps already beginning the long slow drift toward its doom, its orbit altered by some forgotten gravitational encounter, by the passage of a massive star cluster or by a small but cumulative perturbation from the galaxy's spiral density waves, changes too subtle to be noticed on human timescales or even on geological timescales but which accumulated over millions of orbits until the inevitable happened, periapsis decreased below the tidal radius, and the star ceased to exist as a coherent object, its material dispersing into the void, half escaping, half returning to fuel a months-long flare that would eventually be seen across the universe as AT2019qiz, a designation in an ever-growing catalogue of cosmic violence, of stellar death and black hole feeding, of gravitational forces so strong they tear apart stars, processes that have been occurring throughout cosmic history. Throughout the billions of years since the first supermassive black holes formed in the cores of the first galaxies, processes that will continue far into the future as stars continue to orbit, as black holes continue to lurk in galactic centers, and as occasionally, inevitably, the two meet in an encounter that transforms millions or billions of years of stellar stability into hours of disruption and months of luminous aftermath, reminder of the dynamic and sometimes violent nature of the universe. At scales far beyond human experience, at scales where gravity reigns supreme and where the fundamental laws of physics operate at their most extreme limits, creating phenomena that challenge our understanding, that push the boundaries of our theories, and that ultimately reveal the deep interconnections between matter, energy, space, and time that constitute the fabric of reality itself. Retry.